right, let's take a look at the following problem, consisting of a ring where two masses can slide along the ring frictionless. And if we look at this mass, for example, when you slide fast enough, then there will be a reaction force on the ring in the outward direction like this, and also here. So the question is, will this ring start moving upwards after a while for a certain angle, theta? And here is my chosen origin. So let's say here is the x-axis and then the y-axis. And we also have a rope or something holding the ring here with a tension force. And there is a force, of course, because there are gravity here. There is gravity down like this, and also for the masses here, gravity downwards. So let's solve this problem. So energy is conserved because there is no friction. There is nowhere for energy to go except between kinetic energy and potential energy of this system. So what is the mechanical energy of the system? Yeah, T is often used for kinetic energy. So that's why I'm having T here. And we have kinetic energy of this mass, 1/2 mv squared, and the same for that mass. So that's kinetic energy, and the ring might have a kinetic energy. If it's moving, then the kinetic energy is the translation energy of the center of mass of the ring, and the center of mass of the ring is in the origin here. So if that is starting to moving upwards, then that will have a certain kinetic energy. Or if we start rotating the ring somehow, then that would be rotational energy about the center of mass, i.e. this point in the center here. But we are not complicating with that kind of thing. And here you have the potential energy. So let's say we have the zero here, then there is a height here, right? Which is the same as that height over here. And if that radius is capital R, then that height here is R cosine theta. And the same for that bead over there. So, and then the potential energy of the ring, yeah, that's mg times the height from the origin, and where its center of mass is. But the center of mass here is at the origin. So as long as that, so there is no potential energy, it's zero as long as its y coordinate here is at the origin, and it hasn't risen up here. So let's take a look here then at the start. At t equals 0, both masses are up here, and then we let them go, and they slowly will then move downwards. And but when they are up here, then there is no kinetic energy because they start from rest. So there is no kinetic energy here. The ring is not moving; it's at rest, and as I already said, the potential energy of the ring is 0 as long as its center of mass is in the origin. So the only potential energy is from the beads. And that's when they are both up here, it's mg times the height, mgr, and then there are two of them. So 2 mgr, right? And at a later point, like depicted here, then this has a kinetic energy 1/2 mv squared. And this also, the sum is of course mv squared, right? And then the ring potentially, here R stands for ring. So the ring is potentially having a kinetic energy upwards if it has started to move. And then you have the potential energy of mg times this height, mg r cos theta, and then the same for the other one, so two of them. And then potentially mg, the height, y value for the ring, above 0. That is, if the ring's center of mass have been starting to move. So it's a very general equation here. But anyway, the fact is, just before the instant this ring moves, it's still situated like this. The y, its y value is 0, and also the velocity. So this is 0. So therefore, we have this equation here. Energy before and energy little bit later is like this, before everything starting to move. So we must have this, and then we can find out the bead velocity squared. It's this one. So let's continue to look at the bead. What kind of forces are acting on the bead? Yeah, we have the gravitational force mg, and when it's moving fast in the circular orbit, there will be the ring will force the bead to move in a circular orbit, and then the ring must produce a force S on the bead in order for it to go in a circular motion. So it is. But on the other hand, so the ring is doing that to the bead, but the bead is doing a similar thing to the ring. So what I'm saying here, yeah, there is contact forces, but one is S vector and then the negative vector due to Newton's third law. And the same is also for the other bead, of course. But what is the center of mass law actually saying? It's saying that the sum of the external forces equals the total mass times the acceleration. And that is what is used actually, is that all the internal forces, like this example here, S and minus, when we sum this, it's just 0. So it is simply irrelevant. It's not an external force. So the only external forces, it's very simple here, really. Look, what do we have? We have mg here, and then you have the capital mg here, and there is a tension force in the string here. So there is nothing else to think about when we talk about the center of mass law. It boils down to this. So it is simple. And when does it come loose? The moment the ring starts to move upwards, then the tension force here becomes 0. Right? As long as there are forces downwards here, there will be a tension. But when this is starting to move upwards, then the tension will be small, will be 0. So that's the condition when the ring can rise. So then the center of mass law becomes very simple. Look here, minus g m plus 2m. But what is that? That is the total mass of the system. Ring mass and the two bead masses. But that's that. So at that moment, the acceleration of the center of mass will be minus g. downwards. Okay, so that looks like a very elegant result, I would say. So let's continue. What is the center of mass, really? And by definition, it's the mass times the ring coordinate. It's center of mass, actually, plus the mass of a bead times its y value, which is r cos theta, but there are two masses, right, divided by the total mass. And up to the exact moment where the ring has not moved, its y value is still 0. So we can skip this. So that simplifies things. So in fact, the y value of the center of mass is given by this formula here. And since here we need the acceleration, so let's take the derivative like this. And then again, one more time. Then you get this expression. And so this is equal minus g. Then minus here and minus over there, get rid of that. So you have g equal this expression. Right? Okay, so we need to know the angular acceleration. So, and that is determined by one bead. The other bead is doing exactly the same thing. So here is one mass with the mg, right? And if I calculate the torque with respect to that point, which we in the picture above call the point A, the torque will just be that distance, the radial distance, and then that part of the force. And if that is theta, you can realize that that is theta, and then this must be mg sine theta. So here you go. The torque is r times mg sine theta, and as long as the point A here is a fixed point, then we know the torque equation says it should be the moment of inertia times the angular acceleration. And for a particle, the j is simply mr squared. The rotation here is an axis here at A, and the distance to the bead is r, so mr squared. And now we find out angular acceleration is this. So we can now insert that over here, right? And then we multiply this r, the capital R in here. And if we do, then it's just g sine theta. So you get g sine theta squared. And we multiplied r here also. And this looks like centripetal acceleration. So that is just v squared over r. And then we use 2. The equation 2 gave an expression about the v squared. And then we get this here. And yeah, okay, try to simplify this expression a little bit here. And now you see we can cancel out g, 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 and then multiply this up and this over there. So this is the case. You get this equation. And in the problem text, it says if the larger ring mass, I mean the ring mass, capital M, equals 0, yeah, what do we get? Then this is 1, so 1 minus 1 minus 1, that disappears. You get 2 cos theta equal 3 cos, you get cos theta equal 2/3. Yeah, and this is theta equal r cos 2/3 over here. So, and the final thing, we should show that the particle masses must be larger than 3/2 times capital M. And the same equation can be used. Suppose we call this the constant k, 1 plus, and we call this x, so 1 plus 2x minus 3x squared. this is what you have here. And let's solve that, and then you get this expression here, and you see it does, its x should be a real number, cos theta. So it only makes a meaning if 4 minus 3k is greater than 0, and then k must be less than this. And since k was equal to this guy here, you will now find the condition for this to be meaningful, that bead mass must be greater than 3/2 capital M, the ring mass. So, problem is solved. Thank you very much.